All right, now solving for the Rx, the forces, this force is actually the force due to the motion of the fluid. So this one is this equation, the density times the flow rate times the change in velocity. Okay, so that's delta V, okay, plus the pressure P1, okay, that's given. That's the 550 kPa, and the area is also given, B1A1. Okay, so now let's substitute all the values. We have 1000 kilogram per meter cube for the density, and the Q is 0.05 meter cube per second, and our change in velocity is just simply 6.09 meters per second. Okay, so this 3 is equal to this term. Now we need to add another forces, or another force due to pressure. So plus 550 kPa. So take note of the units. This is in kPa, and we have to convert this to pascals only. So that's 1000 pascal is equal to 1 kPa. Right, times the area, which is 8.213 times 10 to the negative 3 meters squared. Therefore, we have a value of 300. Okay, this one, that's 304.5 newtons, plus this term would be 4,517 newton. Therefore, Rx, okay, so that would sum up. This Rx is just equal to 4,822 newtons. Okay, so we have the Rx. Then what's left is, because it says here, find the forces exerted in the elbow. So we can now solve for the R sub y. For R sub y. Okay, applying the equilibrium equation. Okay, so summation of forces y is equal to 0, and therefore this is our y, which is just the Fy, the force due to the motion of the fluid, and the pressure force, which is going downwards. Okay, that's the pressure force. And then our R sub y. Okay, so Fy plus R sub y minus the pressure force is equal to 0. We have this Fy, since we have the same velocity, we have the same velocity because we have the same area, the inlet area and then the outlet area are just the same. So we have the same velocity, and therefore we have the same value, except that this one would be negative. So therefore R sub y is equal to 4,517 minus 304.5, and that's equal to 4,212.5 newtons. Okay, so if we do a recap on what we did, is this problem is actually to find the forces that's in x and y direction. Okay, and we have a pressurized system, so we have to include the force exerted due to this pressure. Okay, so what we did was to draw first the free body diagram, then expose the forces so that we can know which term can we solve directly. Okay, so we did next is to solve for the flow rate, the Q. I mean, is to convert the Q because it's given in liters per minute, and we have to work in cubic meter per second. So we have to convert this flow rate because we need that in solving our velocity. So once we have the velocity, then we can actually find the forces we can find, or we can substitute the value here in this force equation. Okay, so since this is stationary, then we have a summation of forces X is equal to 0, and then we sum them up algebraically, and then we found out that Rx just 4,822 newtons. That's along the x-axis, and we also did the same procedure for the y-axis. Okay, now let's do our last problem for this conservation of momentum, or the force equation. But this one, the problem is this one involves motion of the solid boundary. Okay, so for the problem, it says here, figure below shows a jet of water with a velocity v sub 1 striking a vein that is moving with a velocity v sub o. Determine the forces exerted by the vein on the water if v sub 1 is 20 meters per second and v sub o is 8 meters per second. The jet is 50 mm in diameter. Okay, so we have a vein right here, and this problem is the vein is actually moving. It has a velocity of 8 meters per second. So the vein is moving in 8 meters per second, but the fluid is flowing in 20 meters per second. And this vein, it has a it curves in a 4 to 5 degree fashion. So we have a fluid that's flowing that's flowing into this direction, and then it will deflect in this direction, and therefore we will have forces also in this entry point and forces and this exit point. Okay, so we have to find the Rx and Ry. It says here, determine the forces exerted by the vein on the water. Alright, now, although this is a situation wherein the vein is moving, we can actually analyze it using the same procedure, or the same method that we already learned previously. But we have to convert the velocity. Instead of using this velocity of the fluid, we have to take into account the presence, or the existence, that this vein is actually moving in 8 meters per second. So somehow we have to take the relative velocity. Okay, so relative velocity, or equivalent velocity. Okay, so compute for equivalent velocity, or effective velocity, I guess, v sub b. Okay, which is just given in the equation. V sub b is just v sub 1 minus v sub o. Our v sub 1 is 20 meters per, right? That's 20 meters per second, and our v sub o is 8 meters per second, and therefore our effective velocity is just 12 meters per second. Okay, so if we have the velocity, we need also the value of the flow rate. So solve for the effective flow rate. So Q sub E is just simply A1, okay, A1 times the velocity, but this time we are going to use the effective velocity. If we want to find the effective flow rate, then we need to find the effective velocity. Okay, so A1, that refers to the diameter of this jet. Okay, so we have this area right here. A1 is just pi times d, which is 50 mm squared all over 4, times the effective velocity of 12 meters per second. And if you do the computation, what you'll get is 0.0236 meter cube per second. Okay, now we have the flow rate, we have the velocity, then I guess we can solve for, or let's draw the free body diagram. For the FBD, So this is our vane, and it bends in 45 degrees. And if we now expose the forces, let's say we have forces going right here and then forces also going right here. Oops. Okay, so this is our intersection point. Okay, so this is our line of action, and if we expose the forces, then what we have here is forces due to the motion of the fluid, F sub x, and this one will be, it's actually or it actually has the same value as Fx, because we assume, or we will assume, that the diameter is the same all throughout, and plus the velocity is the same, and therefore the value would just be the same. Okay, so we have a 45 degrees angle here in our reaction R sub x and our R sub y. Okay, so F sub x as well. We'll just write F sub x, or the F value. Okay, so summation of forces x is, okay, let's write here, solve for Rx. So summation of forces x, since although this is moving, but since we compute the effective or the equivalent velocity, then we can analyze this as the stationary object. Okay, so summation of forces x is equal to 0. Therefore, F sub x, so that's it. F sub x is equal to minus. Okay, so F sub x, and let's assume that every force going to the right is positive, and therefore this Rx is negative, minus Rx, and of course the x component of this force, that's going negative, so minus, that's minus, or let's just write this as F, okay, so that we'll will not be confused. Okay, so that's just F cosine 45, okay, is equal to 0. So Rx, we transpose this Rx to the right hand side, so what we're left is F sub x minus F cosine 45. Okay, so, and since Fx and F, they're just the same, then I guess we can factor this out. Okay, so again, please take note that in this problem, it just happens that they're the same because we'll just assume that they have the same diameter. The jet diameter is 50 mm, so they have the same jet diameter, and since they have the same flow rate, and therefore they have the same velocity. Okay, so F is 1 minus cosine, okay, 45. Now what is F? What is F? That's just equal to the density rho times Q times what else? Rho Q times the velocity, right? 1 minus cosine 45. Except that our velocity here should be the effective or the equivalent velocity. Okay, so substituting now all the values, 1000 kilograms per meter cube, okay, times the flow rate. Okay, the flow rate is 0.0236 meter cube per second, times the effective or the equivalent velocity of 12 meters per second, right, times 1 minus cosine 45. Okay, and that's 83. All right, 83. What's this? Kilogram meters per second. That's 83 Newton. Okay, so solve for R sub y. So summation of forces y is equal to 0. Okay, so all forces that's going up, we'll assume that it's positive. But I guess here, if we have this going upward, this r sub y should be going downward. Okay, so r sub y, or f sub y minus r sub y is equal to 0. Therefore, r sub y is equal to f sub y. Now, what is f sub y? It's just the same as the rho QE times delta VE times the sine 4 to 5. Okay, so that's the vertical component of this force. And therefore, this is 0.0236 times 12 times sine 4 to 5. And this is equal to 200 newtons. Okay, so actually there are still many problems that's related to these forces, or solving the forces isn't just by the fluids or the solid boundaries, but there can also be a, let's say, a rotational motion that's involved. So we'll just left with this topic and then move on to our next topic on internal flows. All right, so I hope you've learned a lot. I guess we have gone this far already, and we are now entering the applications. I mean, in the next video we'll be discussing the details on the viscous nature of flow, specifically the pipe flows. And then the following weeks we'll be discussing applications in open channels, and then the external flows after that. So all right, so see you in the next lecture.